Okay, guys, this is what we're going to be focusing on this week, the law of conservation of energy. We'll take that stuff that we learned about work, kinetic energy, gravitational potential energy, and we're going to apply it to solving using the law of conservation of energy. Now, there is one other type of energy we're going to have to use here. We're not going to go into it too deeply, just use it as needed, and that is elastic potential energy. And it just has a formula. I usually write it as ES for, usually it involves a spring. So when you compress a spring, you store energy in it. It's equal to 1/2 kx squared, where k is the stiffness of the spring, and it's in newtons per meter. It's the number of newtons of restoring force it would have per meter that you stretch or compress it. And then x is the stretch, and it's measured in meters. 1/2 kx squared works a lot like the kinetic energy formula. We'll probably use it sparingly, just there'll be a couple questions that involve compressing a spring. So here's the law right here. Energy cannot be created or destroyed, can only be transformed from one form to another without any loss. That is the law of conservation of energy. Total of energy of a closed system always remains the same. So take a ball bounce, for example. When you're holding the ball before it bounces, it has just one type of energy, gravitational potential energy. As it falls, it still has some gravitational potential energy because it still has some height, right? As long as you have height, you have gravitational potential. But now that it's moving, it also has kinetic energy. Actually, I'm going to take out these arrows and just represent that now it's moving, and that is why it has kinetic energy. When it reaches the ground, just as it's hitting the ground, it has a maximum kinetic energy. Now it has no gravitational potential energy. So what we did is we went from gravitational to gravitational and some kinetic energy to all kinetic energy. Then the ball interacts with the ground for just a split second. Then it starts to go back up. I'll put an arrow there. It's got some kinetic energy once it's moving. It's got some gravitational energy because it's up above the ground. And then it reaches its new max height, where it's all just gravitational potential. Again, no kinetic energy. We're just going to make a mental note right here that the ball initially is higher than it is now. If you drop a ball and let it bounce, no matter how bouncy a bouncy ball you have, if you drop it, it never hits the ground and comes back up to the exact same height. So what's happening here? We've got our gravitational to kinetic and gravitational, then to all kinetic. But it doesn't get back up to that same height. So what's happening here, you've got a kinetic energy of 0 and a gravitational energy of 0. 0 kinetic energy because while it's interacting with the ground, it's not moving. It's got no gravitational energy because it's got no height. So then what does it have? If I just kind of erase this, as always, pause this video if you want to jot anything down. What it's doing at that point is it is storing elastic potential energy. I drew the ball kind of compressed there, at least I attempted to draw it kind of compressed, because the ball stores elastic potential energy when it kind of squishes a little bit as it interacts with the ground, and then it bounces, it springs back up. Now, we already said that there's no loss. Well, this clearly shows a loss. I got more gravitational energy at the beginning than I do at the end. That appears to be some loss. So something happens. There's another transformation that we're missing. And it's in that interaction with the ground again. If you hit the ball on the ground, what comes out of it? Well, there's some sound. And sound's a type of kinetic energy. And also, we get some heat lost to the ground. So there's no energy lost. The energy is not destroyed, but the energy can leave the ball. And that's what's happened here. So it says the total energy of a closed system always remains the same. But if you're bouncing a ball, that is not a closed system. It is an open system, because that ball, because energy is getting out of the ball and leaving the ball, and you can't get that sound back. You cannot get that heat back into the ball. So there's a typical energy transformation. Now, next we're going to focus on mechanical energy. And mechanical energy, at least for this course, is just three things. It's gravitational potential, it's kinetic energy, both covered last week, and now there's this new one that sometimes will come up, which is spring or elastic potential energy. So we can create simple systems to show the total energy being constant. A ball bounce is not one of those. So mechanical energy, again, includes gravitational, kinetic, and elastic energy. And in these simple systems, the total energy before is equal to the total energy after. So what I'm using here as subscripts is T is for total, and 0, I don't know why, is the initial. And if you hate that, feel free to change it up. Initial, there we go. And then F is final. When we were doing kinematics, we used 1s and 2s for final and initial, right? So I don't know. Most textbooks use for energy 0s and Fs for initial and final, but if you don't like that, go to 1s and 2s. It works exactly the same. So if the total energy initially of a system has to equal the total final energy of the system, that means the sum of the kinetic, gravitational, and elastic, which we're calling that ES this year, the sum has to be the same before an event and after an event. So kinetic final energy, gravitational final energy, and the spring final energy. Now, I'm not going to give you any systems that involve all 6 of these energies all at once. Let me show you an example of something that we will do. So here's a roller coaster. Just take a second to breathe it in. The mass of it is 1,000 kilograms. The velocity is 10 meters per second at point A, and it's going to go to point B, and then point C, then point D, then point E. So part A says find the maximum speed. So the maximum speed, one thing to note is that the maximum speed will be right here at point C. That is going to be your max speed. Why? Well, if we assume there's not going to be any loss when we are here, then that's the lowest point. So your gravitational energy is going to be at 0 at point C because it's all the way at the ground. It's going to speed up through B and reach a maximum speed at C. It's going to slow down as it goes back to D, and then finally speed up a little again as it goes to point E. So we're dealing with point C and point A. We're going from A to C. So let's start it up. So to solve a conservation of energy problem, you go total energy initial equals total energy final. That's where you start. Actually, I'm going to write right over top of this picture so I have space to do this. So total energy final initial equals total energy final. And then I just got to think about all the energies I have initially and finally. So initially at point A, it has some gravitational energy. How do I know that? Because it's got some height above the ground, the 6 meters. All right, so I've got some EG initial, EGO. Plus, is it moving at point A? It does. It says it's moving at 10 meters per second at point A, so I know I've got some kinetic energy initially. When it gets to point C, does it have any gravitational energy left? No, it doesn't. It is all kinetic energy, so you go EK final. That's your equation. This is about as complicated as it will get for you today, having to deal with 3 energies at once. So remember from previous lessons that EG is equal to mgh. So I'm going to say its initial height, and EK, kinetic energy, is equal to 1/2 mv squared, mass times velocity squared, and I'm going to put a 0 there too to tell you that's the initial velocity. And after it reaches point C, it's got just kinetic energy, so mv squared again. But now I'm going to put an F with the V to denote that that's the final velocity. All right. And now that I think I'm going to have enough space to finish, I'm going to move down here. We're off the diagram. And I'm just going to start subbing things in. What's the mass? It's 1,000 kilograms. What's G? It's 9.81. What's the initial height? It's 6 meters. It says so on the diagram. Plus 1/2, mass is 1,000 kilograms, and the initial velocity of that roller coaster is 10 meters per second. It says so in the diagram. Don't forget that that's squared. That's kind of the most common thing that people forget here. 1/2, 1,000, and V final squared. This is what the question wants us to find, is V final. So then you just start plugging numbers into your calculator. So the first thing I'm going to do is go to 1,000 times 9.81 times 6, and it equals 58860. Plus, I'm going to solve the next one. 1/2 times 1,000 times 10 squared equals 50,000. 1, 2, 3. Equals over here, 1/2 of 1,000 is 500. And then I got V final squared. I'm just going to make a nicer 500 for you. So on the left side, I've got my 58,860 plus 50,000. And it makes 108,860 equals 500. V final squared. I'm going to divide by 500, and then I'm going to square root it to figure out what V is, and it gives me 14.8. My final velocity is equal to 14.8. This is a good time for you to pause this and make sure you can punch that in and get the same answer. I'm not going to do this one right now. I'll show you some more examples of this. This is what we're working on all week. So on Wednesday, I'm just going to do more examples like this. Maybe go to a little bit more depth, and then we'll do some more work on that. Anyways, so 14.8, pause the video, make sure you can get that, and we'll do some more of these. So I'm going to skip A, read this one to you. So a boy throws a 0.5 kilogram stone at 1 meter per second towards the ground from the top of his roof, which is 3.2 meters high. How fast is it going when it hits the ground? Believe it or not, this is almost the same question that we just solved. We're going from roof to ground, from here to here. It starts out with some gravitational energy. Why? Because it's up high, and it's also got some kinetic energy because it's moving. When it hits the ground, it's only got kinetic energy, no gravitational energy left. This is the final, and these are the initials. So that's all you're doing. You're going EG initial plus EK initial equals EK final. The same equation we set up before. I'm going to have some different numbers, of course. 1/2 mv squared initial equals 1/2 mv squared final. Plug in some numbers. It's 0.5 kilogram, so 0.5, 9.81 times that initial height, which is 3.2 meters, plus 1/2 times 0.5 kilograms, and times that initial speed of 1 meter per second, and I got to make sure that's squared, equals 1/2 kilogram times V final squared. Probably I have the skill to punch all that stuff in the left at once, so I'm going to go 0.5 times 9.81 times 3.2 plus 0.5 times 0.5 times 1 squared equals 15.946, and that's equal to 0.25. That's just half of 0.5, V final squared. So now I'm dividing it by 0.25, and then I'm hitting square root. And in the end, I'm just finding a space to write my answer. My V final is 7.99 or even 8.0 meters per second. So that's pretty much the same as the first, and I'm just not doing part A because I only have room on these slides to show you one solution. I want to make sure I do one with a spring just in case it comes up. Oh, there we go, right here, guys. So I'll do those examples later in the week if necessary. Probably I'll come up with some more examples closer to the problems you're going to have to solve later on this week, but we'll see if there's a desire to see more examples, I'll do more of those. So a ball bearing of mass 500 grams is up against a spring that's compressed the way that it shows right there, and then it's going to be released and go up the ramp, and it says what height does it get up the ramp. That's what we're going for here. It gives me a stiffness of the spring that is compressed against, and it also gives me how much that spring is compressed. All right, so this will feel a little awkward the first time we try this, but if we go, okay, total energy initial equals total energy final, what types of energy does this have when you're just holding it up against that spring? It's got no kinetic energy because it's not moving until you let it go. And it's got no gravitational energy because it's got no height. So all it has is some stored elastic potential energy. And then you release and it goes up the ramp. It's going to get about to there. What types of energy does it have when it gets up to there? Well, of course, it's going to have gravitational energy now because it's got height. And it can be height, we're going to be measuring the height right here. When it gets to its max height, will it have any kinetic energy? Well, no. When it gets to a max height, it's going to stop before it rolls back down the ramp, back towards its starting spot. So all you have is EG final when it gets to its max height. We're going from start to finish. So what are the formulas? 1/2 kx squared, that's the formula for elastic potential energy, and then mgh final for the final height that it gets up to. I'm going to sub my numbers in. Well, I'm going to erase some stuff. Pause the video at any time if you want to add something. I'm going to sub my numbers in right here. 1/2, 250 for the spring stiffness, and then 5 centimeters, but that has to be in meters. So that is 0.05 meters. Make sure you get that right. Don't forget that x is squared. Then I need the mass, 0.500 kilograms. Oh, I converted that 500 grams to kilograms. And by 9.81 and times that height. I'm going to calculate that stuff on the left. It's 1/2 times 250 times 0.05 squared, and it equals a really small value. 0.3125 equals 1/2 of 9.81 is 4.905 times h. So I got 0.3125, and then I just got to divide it by 4.905. That final height is going to be 0.064 meters or 6.4 centimeters. Most of the questions are just like that, where you're just doing one thing. I do want to go back to one more. I don't know. Yeah, this one right here. This one right here. I'm just going to exit here for a second and delete. This line right here is just to give me some space for doing this. If I can, maybe I can't do that right now. Yeah, that'll work for me. So basically what I wanted to do with you guys here is just say, a ball is thrown up at, 12 meters per second. Sounds good. Find the max height. That's it. That's all you gotta. That's all you need to know. We're going now from ground. Oh, good. I already got a ball there drawn for me. A ball. We're gonna fire it up in the air. As you know, it's gonna slow down and reach a max height. Now, you guys have done this using concepts of kinematics before, with like V1s, V2s, A's and T's and D's and stuff like that. But I want you to do this using the law of conservation of energy. It's actually easier. So I'm going to go ET initial equals ET final. All I got is that speed, and you're going to see that it's going to work out for us. So in the beginning, you're firing it up at 12 meters per second. So of course it's got some kinetic energy, but it's not off the ground yet. So it's got no gravitational. When it reaches its max height, it comes to a stop or to rest. So it's going to be all gravitational because it's got height at the end. So this is it. That's all you got to deal with. So you go 1/2 mv initial squared equals mgh final. And if you're really sharp, you might be thinking, well, he didn't give us a height or a mass. He's going to have to give us a mass. But I really don't, because if I've got a mass on the left and the right, I can actually cancel that out. It'll divide out for me. I'll leave it in there just for now, but you're going to see that it cancels out. So let's leave it in there and just see what happens. So I got the mass there, and I got 12 meters per second, and it's squared. And then over here, I've got the mass again, and I got 9.81 and times the height. All right. So 12 squared is 144. Well, let me work it out. Times a half is 72. So I got 72 m on the left, and I got 9.81 m on the right, and times h. So of course, a good math teacher would say, okay, divide both sides by 9.81 m. That gets rid of that. That gets rid of that. Keeps the h by itself. The m's divide out, and I got 72 divided by 9.81, and that's what's going to get me the answer of 7.3 meters. Now, a lot of people don't like that. So, like, even during tests in the past, when someone says, hey, we need a mass, we can't solve this without a mass, I say, just use 1 kilogram. Use whatever mass you want. It won't make any difference if you use 1 kilogram, 500 kilograms. You'll get the same answer no matter what mass you use. The only time that you really need a mass is if you're using elastic potential energy, because there is no mass in that, so it can't divide out the same way. Anyway, I wanted to make sure I did like a max height problem here. Showed you that the masses can cancel out. I'm going to exit here again. And I'm actually going to open up what your assignment is going to look like right here. Get you onto your class. And let's look at tomorrow's scheduled work on conservation of energy. So here's what the document looks like. There are 11 problems, and you basically have all week to work these out. All right, some of them are super easy, and some of them are hard, and there's a mixed bag, really. So for tomorrow, or for the first half of the week, I just want you to try and do the first 5 of these, and we'll do the second 6. So try and get those done today and tomorrow, and then Wednesday, Thursday, Friday, do the other ones. Now, if you get them done quick, then that's it. That's all the work you have to do this week. If you scroll down in the document, there are answers. Now, you might question the methods that they use. It doesn't always match the way that I showed you in class or in this lesson. But the answers, I think, for the most part, are good. All right, so you should be checking as you go. If you don't know how to do something, don't know how you got the answers, no problem. Just email me, and I'll send you a mini video of me solving it, or a screenshot of me solving it, or something like that. All right, so that's going to be all for now. Just try and get up to number 5 by Wednesday, and then we'll do 6, 7, 8, 9, 10, 11 on Wednesday, Thursday, Friday. All right. I think that's it, guys. Good luck.